Seer, online context learning for fast synchronous LLM reinforcement learning.
So we are jumping straight into a paper that really gets its hands dirty with what a lot of ML engineers would call the most stubborn problem in LLM reinforcement learning.
Yeah, the rollout phase.
Exactly.
And the scale of this problem it's just staggering for anyone who's actually managing RL infrastructure in production. With synchronous training, you're always alternating between data generation, the rollout, and the model update.
And that rollout part is the bottleneck. We're talking 63% to, in some cases, a massive 87% of the total iteration time.
It's just wild. And this whole inefficiency, it's pretty much entirely driven by this shift towards, these complex long generation things like chain of thought reasoning.
Right. And that creates these highly variable, super long outputs, which leads to two huge headaches, just catastrophic long tail latency and, frankly, abysmal resource utilization.
But the core insight of Seer is, well, it's almost deceptively simple. They just exploit the contextual similarities, specifically length and pattern among requests that already belong to the same group in algorithms like GRPO.
And they turn that insight into this really elegant three-part solution. First up is divided rollout. It basically transforms these huge monolithic jobs into small, manageable chunks.
Which allows for dynamic load balancing and way more stable memory management.
Then there's context-aware scheduling. This uses some clever speculative requests to predict the length of other jobs, which lets them implement a kind of longest job first policy to kill that long tail.
And the third piece is Adaptive Grouped Speculative Decoding. This is a model-free approach, which is key. It uses a data structure, a compressed suffix tree, to leverage pattern context inside these groups and generate much, much better draft tokens on the fly.
The impact. It's a huge gain.
Right.
We're talking a 74% to 97% improvement in end-to-end rollout throughput.
And it just crushes that long tail latency, reducing it by 75% to 93%. This isn't just a small tweak. It feels like a fundamental fix to a scheduling nightmare.
Okay, so before we get too deep into the solution, we really have to appreciate just how bad this bottleneck is. If you've ever tried to scale on policy RL, the rollout phase, where the model is just generating trajectories, is where all your time just evaporates.
The paper's data is pretty damning on this. It says it accounts for 87% of the time for Kimi K2 and 84% for Moonlight.
Think about that. That means your very expensive accelerators are sitting there, basically idle or starved, for 8 out of every 10 minutes.
And that inefficiency is directly tied to needing these long generations. You need chain of thought to train an advanced reasoning model, and that just means you get these unpredictable, enormous responses.
The paper shows Kimi K2 responses peaking near 98,000 tokens.
98,000. Just imagine trying to batch and schedule that kind of volatility.
Well, that volatility creates the first huge engineering headache, the KV cache memory footprint. It's just all over the place. A single long request can see its KV cache just balloon from, a few hundred megs to tens of gigabytes.
So when you have a bunch of those running at the same time, the inference engine is forced to do something drastic. It either has to shrink the batch size down to nothing or
worse, trigger a full preemption.
And preemption is the real killer, isn't it?
Oh, absolutely. It's not just a slowdown. Preemption means you're throwing away minutes of work, clearing the KD cache, and then you have to pay the full cost of a pre-fill operation just to start the request over. It can completely gut your throughput.
And then on top of that, you have the second challenge, the infamous long tail effect.
Right. Because the output lengths are so heavy-tailed. Most are short, but a few are just absolutely massive. Those last few long-running requests end up monopolizing all the accelerators.
We've all seen that graph, right? The one where utilization just drops off a cliff. Figure 3 in the paper shows this long tail phase can account for nearly half of the total rollout time in baseline systems. You're just waiting on one giant job to finish.
While all your other compute just sits there, idle. It's incredibly wasteful.
And just to cut off the obvious question, why not just use asynchronous RL? The authors make it clear that synchronous on-policy RL is still critical.
It is. Async methods can hide latency, sure, but they introduce off-policy learning, which can lead to distributional skew. The short, fast samples start to dominate, which messes with reproducibility and can even hurt the final model quality.
So Seer is all in on solving the harder but higher fidelity synchronous case.
Okay, so that's the problem space. Volatile memory causing preemption and length variability causing this massive long tail. Now let's pivot to Seer's key insight, which really comes from looking at the training algorithm itself, specifically GRPO.
Right. Algorithms like group relative policy optimization are pretty standard. The key thing is that GRPO generates a group of G responses, usually, what, like 8 to 16?
Yeah, somewhere in that range.
Right.
And they're all conditioned on the exact same prompt. But existing serving systems just treat these as, G completely separate, unrelated black boxes.
And they're not unrelated at all.
Not at all. And that's what the Seer authors realized. Because they all share semantics and structure from the same input, they have this powerful, exploitable structure.
They break this down into two, what they call contextual signals. The first one is length context.
Which is so simple but so powerful. If one response in a group ends up being really long, the other responses in that same group are just overwhelmingly likely to be long too. Figure 4 in the paper shows this really strong correlation.
So that gives you an instant online predictor for how much work a job will be.
Exactly. And the second signal is pattern context. I mean, they're generating similar language from the same prompt, so of course they're going to share local token patterns.
And that's the key to their model-free speculative decoding approach, which accelerates the actual token generation.
Right. So let's trace how they use this, starting with the foundation, which is how they fix the memory and preemption problem. They call it divided rollout.
And this is a really radical shift away from that monolithic group-level scheduling.
Yeah, instead of treating a group of 16 requests as one giant, unpredictable job, Seer first breaks the group down into individual requests, and then it goes even further and divides each of those requests into multiple, incrementally schedulable chunks. I think they use a chunk size of like 8K tokens.
It's a brilliant move. That fine-grained decomposition means the scheduler is now dealing with these smaller, much more predictable KV cache footprints.
And because it can maintain this constant fine-grained view of memory, the system can dynamically compute the maximum concurrency without oversubscribing.
So without triggering those ruinously costly preemptions.
Precisely. And this explosion in granularity, you're going from one scheduling decision per group to potentially, hundreds of decisions. That's what enables true dynamic load balancing. When a chunk finishes, the system just re-enqueues it and picks the least loaded inference instance in the entire cluster.
But hold on a second. Moving a request chunk between different instances sounds like it would introduce massive overhead. I mean, how do they handle the cost of migrating that KV cache state?
That's a great question, and yet it requires some serious infrastructure. They're relying on a globally shared KV cache pool, something built on concepts like Mooncake. It's usually a 2-tier system with DRAM and SSD offloading.
So the KV cache is globally accessible.
Exactly. So that eliminates the need to recompute the expensive prefill operation after you migrate a chunk. That shared abstraction is what makes the whole load balancing scheme possible. Without it, the idea would fail completely.
Okay, so with that fine-grained structure in place, they can go after the second big problem, the long tail. Which brings us to context-aware scheduling.
Right. And this is designed specifically to implement an approximate longest job first, or LFS, strategy.
LFS is optimal for maximizing density, but the whole problem is you don't know the job length ahead of time.
So Seer uses that length context correlation to estimate it. And they do this with something that they call the speculative request mechanism.
This is clever. They mark the first request of each group as speculative. And this request gets put into a high-priority queue that, kind of paradoxically, uses shortest first scheduling, SFS.
Think of it like a probe. You want to get information back as fast as possible. SFS quickly finishes off the shortest speculative requests first, and in doing so, it reveals the maximum observed generation length for that group, which they call L hat G.
So you use SFS just to get a quick data point, and once you have that maximum length, L hat G, it becomes the online predictor for how long the rest of the requests in that group will take.
That's it. Once those speculative requests are done, or even just in flight, the remaining requests are scheduled using the approximate LFS policy. You prioritize the groups with the longest predicted length.
And that ensures the big, long jobs start early and finish closer in time to the short ones.
Which maximizes your batch density and finally gets rid of that painful long tail gap where all your resources are just sitting idle.
The paper says they got an 87% reduction in tail latency with this. That sounds almost too good to be true. I mean, doesn't all this juggling of SFS and LFS and migrating chunks introduce its own overhead?
You'd think so, but the ablation study suggests it's pretty negligible because that correlation signal is so strong. They actually showed that this context-aware scheduling achieved 95% of the throughput of an Oracle scheduler.
An Oracle that magically knew all the output lengths in advance.
Right. So that 5% gap is basically the only cost you pay for doing the online estimation. Hitting 95% of optimal performance with a real-time system is, pretty convincing evidence that this thing works.
Okay, that covers scheduling and memory. But there's still the third mechanism, which actually accelerates the token generation itself. Adaptive Grouped Speculative Decoding.
Yeah, and this is important because traditional model-based speculative decoding really struggles in a continuous RL loop. For one, you have rapid model drift.
Meaning the main LLM is constantly being updated.
Exactly. So your static draft model quickly gets out of sync, and the acceptance rate just collapses.
Plus, running a second dedicated draft model, even a small one, adds latency and, crucially, GPU memory overhead. You solve one memory problem just to create a different one.
So Seer's solution is to go completely model-free, based entirely on that pattern context from the group, and they manage it with a distributed grouped draft server, or DGDS.
So if it's model-free, how does it generate draft tokens that are actually good enough to be accepted by the main model?
They use a data structure called a compressed suffix tree, or CST, as the backbone. You should think of it less like a predictive network and more like a hyper-efficient dynamic dictionary. The DGDS just aggregates all the token patterns happening across all 8 to 16 requests in the same group and stuffs them into the CST.
Okay, so the system is building a live local dictionary of token sequences that are being generated right now by its peers in the same group.
You got it. So if request A just generated the capital of France as P, and the other requests are on similar topics, the CST uses that shared context to confidently predict what comes next for request A. It creates this synchronized draft model that's perfectly aligned with the target model because it's built from the target model's own recent outputs.
That's really cool. And the data shows it works.
Oh yeah, the empirical data is fantastic. Using pattern context from the 15 other responses in a group increased the mean acceptance length of the draft tokens by up to 119%. You're just doing more useful work per inference step.
And the adaptive part. How does it change its behavior based on the system load?
This is where they come back to optimize the long tail phase again. The system is always monitoring the current concurrency. And based on that, it adjusts the maximum draft length and how many paths it explores.
So when things get quiet. Exactly. Figure 12 shows that when concurrency is low, which happens precisely during that painful tail phase, the system starts generating more draft tokens per step. It gets more aggressive.
So it preferentially accelerates the hardest, longest-running requests right when the system needs that boost the most.
Right. It increases the mean acceptance length to over 3.5 tokens during that phase. And this synergy is super effective. This adaptive decoding component alone added another 30% to 44% performance improvement on top of the scheduling optimizations.
Looking at the overall evaluation, the results hold up across serious production-grade models like Qwen 2 and Kimi K2. We're seeing end-to-end throughput gains between 74% and 97%.
And for the engineers who are wrestling with their production queues, that 75% to 93% reduction in tail latency is the real win. It solves that resource monopolization problem that used to eat up half the rollout time.
And crucially, it does this while using existing tools like VLLM and staying strictly on policy so it maintains that algorithmic fidelity. The system stability is another big takeaway. Baseline systems have this huge variability in completion time because of randomness. Seer's fine-grained approach just smooths all of that out, which leads to more predictable and stable deployment cycles.
So in the end, Seer really transforms the synchronous RL rollout. It takes it from this monolithic, memory bottlenecked mess into a highly optimized, context-aware pipeline.
And it all came from recognizing that the workload itself, the GRPO algorithm, was carrying these intrinsic structural clues that our general-purpose serving systems have just been completely ignoring.
And that really leads us to the final provocative thought for you to think about. Seer got these massive gains by leveraging the inherent structure of GRPO. So what other domain-specific, policy-driven structures are we currently ignoring in our general-purpose LLM infrastructure that could yield similar massive performance gains if we just took the time to learn the context and build algorithm-aware systems?
Yeah, if the gains from just identifying group context are this high, the implication seems pretty clear. The next big leap in LLM efficiency probably won't come from just bigger models or faster GPUs, but from smarter system designs that are actually tailored to the specific algorithm you're running.